Hey friends, welcome back to our series, our Diploma Prep for 30-1 series. We are now beginning, this will be video 10 um, on exponents and logs, okay? So as far as our weekend course goes, this would be the beginning of part 4. But in our video series, this is the second last video. Video 10 will be on exponents and logs. And then video 11 will be on perms and comms. And then that will wrap up the course, all succinct in 11 videos. I hope you guys are finding these helpful. I am very much enjoying bringing them to you. Thanks for watching and thanks for subscribing. I really appreciate it. So let's get going on talking about some exponents and logs. Okay, so just some basic stuff first as way of review. An exponential function, I'm just going to hide my head here for 1 sec. An exponential function is a function that exists in the form y equals a times b to the x. All our standard transformations can be applied, and I'm going to walk you through a question that applies them all in a minute. A is the y-intercept, and then in an application question, that would be considered like the initial value of whatever, like our population or the initial value of a car that's going to depreciate or something like that. If b is greater than 1, it's a growth function. And if b is in between 0 and 1, it's a decay function. Now, I just want to talk about this for a sec, because that's a really important sort of feature here. Say I was your actual teacher and your parents came to parent-teacher interviews and I looked at them and said, hey, your kid has changed 100% since this course has started. Your parents would be all smiley because they heard the word 100% and they're like, oh, I'm so proud of my kid. But actually, mathematically, I just said, you did jack all. Because a change of 100%, think about that from a multiplicative standpoint, a change of 100% is 1. Anything multiplied by 1 is itself. If I say you change by 100%, I'm saying you didn't change at all, okay? In order for you to grow, you have to be larger than 100%, or then as a decimal, you have to be larger than 1. In order for you to shrink, you have to be somewhere between 0 and 100%, or as a decimal, somewhere between 0 and 1. Okay, so if I said something like a 20% growth, that rate is going to have to be 120%. It's 20% on top of that benchmark of 1. Okay, whereas if I said, say, a 25% decay, what that really means is I'm 25% below the benchmark of 100%. So that would be 75% or 0.75 as a decimal. Okay. So when you compare the graphs that I have below this at the bottom of the screen there, the blue graph would be a b value that is greater than 1, so it's a growing graph. And then the red graph would be a b value that's somewhere in between 0 and 1. E value can't be 1, because think of it, it's the rate, right? What's 1 to the 7? What's 1 to the 10? What's 1 to the 18 billion? It's always just going to be 1. It's just going to be a flat line. Okay, so that doesn't actually produce an exponential graph. The domain of all of these is x is a member of the reals, and the range will be y is greater than 0. Careful that it's not equal to 0 there. And that's because of the next statement, there's a horizontal asymptote at y equals 0. Now, friends, of course, you've heard me preach this in other videos. Don't you dare ever write HA on a diploma. If you're talking about a horizontal asymptote, you need to write out the word horizontal asymptote, okay? Okay, perfect. Now I'm just going to clear that ink and we'll go and compare that conversation to an exponential function. Again, I'm just going to hide my face for a quick sec. Sorry, I said exponential. I meant logarithm. A logarithmic function is a function that exists in the form y equals log base b of x. Now, again, all our standard transformations can be applied. And again, if b is greater than 1, it's going to be a growth function. So that would be the blue graph. And if b is in between 0 and 1, it'll be a decay function, and that will be the red graph. Now, there is one thing before I keep going here that we want to talk about, and that is this looks like this graph stops here. That's just the calculator not really understanding what to do about a vertical asymptote, okay? If you are to draw these, you are going to want to keep that going up right by that vertical asymptote forever, or down right by that vertical asymptote forever. Okay, so just be careful that you're not misinterpreting what you're seeing in your calculator. You have to remember your calculator is just a set amount of pixels, so at some point it can't get any closer to the horizontal asymptote, so the computer program just stops it. The logarithmic graph is a inverse function of an exponential graph. Therefore, everything that was x switches to y, and everything that was y switches to x. So what you'll notice in this next statement here, the domain is now x is greater than 0. That was the range in the exponential function. And now the range is y's member of the reals, which was the domain in the exponential function. Okay, and now I have a vertical asymptote. Again, don't ever write VA. Vertical asymptote at x equals 0. Okay. So logs are the inverses of exponents. This means a couple of things. Mathematically, taking the log of a number will undo the exponent, much like dividing both sides of an equation will algebraically undo the multiplication. Visually, a logarithmic function will look like a diagonal reflection of the equivalent exponential function, or not the equivalent, but the inverse exponential function. Okay. All right. We are also able to use logs to switch an equation from being written in exponential form to being written in log form. Just gonna hide my face there for 1 sec. This is not taking the inverse, only switching forms. So this is actually a really important point. These guys here, I'm not taking the inverse. I'm merely switching forms. Now, to switch forms between exponential form to logarithmic form, the following happens. The base becomes the base, okay? The dude that was by himself, so the dude, I always say the dude that was free, is now going to become locked. So the y was free, and now he's locked in as an exponent. And then the dude that was locked, this x was locked in as the exponent, he's now going to become free and become the x all by himself. Okay. Please accept my apologies. I just kind of listened to what I said. I think I called this an exponent. This is not an exponent. The y was free. He's now going to be locked into the log, not locked in as an exponent. Please forgive me. Okay. So as we just unpack this for a second, I want to just make sure you see the difference. So from here to here, I'm taking the inverse. Okay, take a look. This is an exponential graph written in exponential form. And then what I've done here is I've switched the x and y. That is what taking an inverse is. Okay, so this is an exponential graph written in exponential form. This is an exponential graph, just written in log form. Okay, this is a log graph written in exponential form, and this is a log graph written in logarithmic form. Now, obviously, it mostly makes sense that we're going to use this and this. We're going to talk about an exponential graph using an exponential equation, and we're going to talk about a log graph using a log equation, okay? But I do really want you to have a good feel about the interconnectedness between, first of all, taking the inverses, and second of all, switching forms, because they are two different things, okay? All right. Awesome. Okay, so below is the graph of y equals c to the x. I'm just going to hide my face for 1 second. That is the blue graph that you see right here, y equals c to the x. Describe the transformations on y equals c to the x that produce each of the following functions. Okay, so in this first one, h of x is c to the x minus 3. Well, what have I done? I've replaced x with x minus 3. That means I've done a horizontal translation 3 units to the right. So when we're trying to figure these things out, really the easiest thing to do is just to kind of map it out. So I know that I had a point right here on my original y equals c to the x. If I now move that over 3 units, 1, 2, 3, it looks like I'm on this kind of orangish reddish graph, okay? But let's take another point and just double check. Let's take this point because it looks kind of friendly to me. If I move that guy 1, 2, 3 units over, 1, 2, 3, I again see that I'm on the red graph, okay? So my description would be a horizontal translation, 3 units right. The domain would still be x as a member of the reals. The range would also be y is greater than 0 because I didn't move it up or down. I would have no x-intercept because again, I'd have to move it down in order to have an x-intercept. Right now, the asymptote is there. And then my y-intercept, well, if I want a y-intercept, I'm plugging 0 in for x. So I get out c to the negative 3, which is the same thing as 1 over c to the positive 3. We never write something with a negative exponent, okay? So my y-intercept would be 0, comma, 1 over c cubed. Okay, in g of x, what am I doing? Well, I see that the b value there is a half, and so that would be a horizontal stretch by a factor of 2. Remember, it's always the reciprocal of b. A horizontal stretch by a factor of 2 about the y-axis. So now if I think that through again, I'm just going to plot points 0, 1. If I take the point 0, 1 and multiply my x value by 2, I should still be at 0, 1, right? Okay, so then let's try this other friendly point here, which is at 4, comma 3. That should turn to 8, comma 3. I'm multiplying my 4 by 2. So 8, comma 3. Yeah, that looks like we're pretty sure that's going to be the green graph there. Okay, so if that's the green graph, we're ready to go. I've got a description of a horizontal stretch by a factor of 2 about the y-axis. My domain would be real. My range would be greater than 0. And I'd have no x-intercepts. And my y-intercept would be 0, comma 1. Now, it is at this point where I'm going to stop and just reiterate the importance of clear communication. I've said it already in this video, but I will say it again. Don't write HS. It needs to say horizontal stretch, and then it should say by a factor of 2 about the x or about the y-axis. I am trying to condense everything into a little table here, so I am abbreviating slightly. My domain and range are not written properly in this diagram. Don't do that on your diploma, okay? Don't say, oh, my teacher told me I could. If I was to write this proper, that would be all the values of y such that y is greater than 0, comma, y is a member of the reals. That would be the proper way to write that on a diploma, okay? Okay, p of x, now I'm looking at a vertical stretch of 2 about the x-axis. So I'd be taking all my y values, multiplying them by 2. If I go back to these two friendly points and just kind of test those, 0, 1 would become 0, 2, and 4, 3 should become 4, 6. So I can see that that is going to be the purple graph in our example here. And so that would be a vertical stretch of 2 by a factor of 2 about the x-axis. My domain would still be real. My range would still be greater than 0. I would still have no x-intercepts, and my y-intercept would now be at 0, comma 2. And then finally, c to the x minus 3 is what's defined as p of x here. So I've taken everything and I moved it down 3. I can clearly, again, if I just take a couple points, 1, 2, 3, I can clearly see here, 1, 2, 3, that this is the pink graph, fuchsia graph. I'm not quite sure what you call that color. I would have a vertical translation 3 units down. My domain would still be real, but my range would now be greater than -3 because I brought everything down 3. My x-intercept is at 4, 0, and I do have a y-intercept now at 0, 2. Okay. I knew my y-intercept was at 0, 2 because your y-intercept will be the a value. Like if I write just where can I write this for you? Y equals ab to the x. We said that a was your initial value. If we've moved it down, what I want you to think about is a is kind of the distance from your horizontal asymptote. It'll be the distance up from your horizontal asymptote on the y-axis, okay? So like, I just want to unpack that a little bit more. I feel like some of you are looking at me like, what did he just say? If I did this 3 times 2 to the x, you're going to tell me that my y-intercept is at 0, 3, right? Because that's my a value. But that's because right now my horizontal asymptote is at 0. If I now said, hey, I'm going to move all that down 4, well, my horizontal asymptote is now at -4. My y-intercept is going to be 3 up from that horizontal asymptote. Okay, so 3 up from that horizontal asymptote is at -1. My y-intercept would be at -1 for that guy. Okay. Okay. The following graph represents log or y equals log base c of x. The x-intercept of y equals log base c of x minus 4 can be written in the form a comma 0. What's the value of a? Well, essentially, I'm taking the graph that I see and I'm moving it down 4. And then I'm being asked, okay, what will be my new y-intercept? So I want to look at where my original graph hits at 4, right? If I think about where my original graph hits at 4, that point right there is going to move down 4, so it's going to be at 10. Okay, so the value of a would have to be 10. Describe the transformations that have occurred to the graph g of x equals 2 times 3 to the 4x minus 20 minus 8 if g of x is the result of transforming an original function f of x equals 3 to the x. State the domain, the range, and the asymptotes of g of x. Okay, well, let's deal with the transformations first. I want you to notice that the 4 hasn't been factored out of the 4x minus 20, so that should really say 4 bracket x minus 5. And then we're going to go 1, 2, 3, 4 different statements here. We're going to have a horizontal stretch by a factor of 1/4 about the y-axis, and then a vertical stretch by a factor of 2 about the x-axis, a horizontal stretch 5 units right, and horizontal translation 5 units right, and a vertical translation 8 units down. Okay, so horizontal stretch by a factor of 1/4, vertical stretch by a factor of 2, horizontal translation 5 units right, and vertical translation 8 down. Now, the domain will be real. The range will be greater than -8. And I will have an asymptote at y equals -8. So domain's real, range is greater than -8, and then I have a horizontal asymptote at y equals -8. Awesome. Okay, determine the y-intercept of the graph of y equals a b to the x plus c. So again, I'm just plugging 0 in for x, right? So if I plug 0 in for x, b to the 0 is 1. So then I'm left with a plus c, which would be the answer c. I'll just hide my face there just in case you didn't fully see the question at home. All right. the inverse of y equals 3 to the x. Now you got to be careful with this. This is where we mix up taking the inverse and switching forms, okay? If I took the inverse of this, I switch x and y. So that would become x equals 3 to the y. Now, that's not what these guys are. So now I have to take this and switch forms. Base becomes the base. So I'm looking at log base 3. Dude that was locked should now be free, and dude that was free should now be locked. So the x is now locked into the log. Y is now free and by itself. Okay, so that is going to look like B. Okay. Right, convert the following into exponential form. Again, just reviewing this whole base becomes the base and the other guys switch jobs, okay? So this is going to be base is 2. This was free, so now it will be locked. 2 to the y equals x. Here, I can't convert this until I've dealt with a 3. I actually have two options for the 3. I could bring the 3 up and have it be an exponent on b. That's one of my power log laws. Or I could just divide both sides by 3. Doesn't really matter at the moment. I just chose to divide both sides by 3, and now I'm going to switch to exponential form. There is no base written here. That is a common logarithm, and that would be base 10, okay? Base 10, so it would be 10 to the a over 3. All right, if I take 5 equals 2 to the x and convert that to log form now, base becomes the base, so that'd be log base 3 of 5 equals x. Log base 3 of 5 equals x. And then in B, again, the 10 is kind of in the way. Rookie mistake, I see lots of kids multiply the 10 and the 2 together. You can't multiply this 10 and 2 together because by order of bed mass, the exponent has to be dealt with before the multiplication. So this guy and this guy have to remain separate. Okay, so let's get rid of the 10 the only way we can get rid of the 10, which would be through dividing both sides by 10. So if we divided both sides by 10, we'd have 3 over 10. Then I can switch to log form. My base is 2, so it'd be log base 2 of 3 over 10 equals x. Log base 2 of 3 over 10 equals x. All right, friends, you guys are rocking this. Match each graph with the appropriate equation. So record the equation for graph number A in the first box. So graph number A, what I want you to notice here, first of all, when I look at all these equations, there are no transformations involved, okay? They're all just base, log, or exponent functions, which means this guy is looking like a growing exponential. So a growing exponential would be with an a value here greater than 1, so that would be 2. Graph B is look like a growing log. So here's a log with a is greater than 1, so that would be 4. Graph D, oh, I guess I should go in order. Graph C, that looks like a decaying log. So that'd be a log graph where a is a fraction, that's number 3. And then graph D, that would be a decaying exponential graph. And so that would be number 1. So my answer would be 2, 4, 3, 1. Okay. All right, evaluate without a calculator. Now, don't let that like stress you out. I'm not here to stress you out. Nobody's ever taking your calculator away from you, okay? The point is, let's just deal with our knowledge of logs and get comfortable with how we can manipulate the logs. So log base 2 of 64, it's very friendly to me if I can think about 64 as being 2 to the something, okay? So if I was to think, what would this look like in kind of an exponential form? I'd be thinking, okay, it's going to be 64 will equal 2 to the something, okay? Now, 2 to the 5 is 32, 2 to the 6 is 64. So that tells me that log base 2 of 64 would be 6, okay? We haven't done a whole lot of this yet, but the other way to look at this is to have actually written it as log base 2 of 2 to the 6th, and then use your power log law, right? This can come to the front, and that would be 6 log base 2 of 2, and then we know that log base 2 of 2 is 1, and so that would give me 6 that way as well. Okay, whatever makes the most sense to you is totally okay by me and totally okay by Alberta Ed. Okay, now this guy, I want to think about log base 10, right? Log base 10 of 1,000. Well, 10 to the what is 1,000? That'd be 10 to the 3. So log base 10 of 1,000 is 3. So I end up with 3 times 3, which is 9. Okay, 3 times 3. Okay, log base 2 of 3. Now, this one says evaluate with a calculator to 3 decimal places. There's a couple different ways you can do this. If you are a Casio kid, you have a log base A of B button. So if you are newer Casio, if you just press your math option, which is F4 on your calculator screen, then you'll see it as F2. Okay. If that doesn't work, Casio kids, you can press option and then more options. Nope, I lied to you. Sorry. You can press option. Sorry, I'm doing it as I talk to you. You can press option and then calc and then more options, and then it'll be F4. Okay, so options, calc, more options, F4. If you're a TI kid, you can press the math button, and I think then you just have to go up 2, and you'll see a command that says log base A of B. If you're an older TI, you don't have that option, but everybody can use the change of base identity. So the change of base identity would say that I can change this to base 10 by going log base 10 of 3 divided by log base 10 of 2. Okay, so the thing you were originally taking the log of goes on the top, and then your original base goes on the bottom. Everybody has a log button on their calculator, so everybody can do it this way. Okay. So there's the change of vars. There's the change of base identity, and that's on a formula sheet for you. Okay, so you should be getting this to be 1.585 when evaluated to 3 decimal places. And then for log base 3 of 3 over 4, same thing, just pushing buttons in your calculator, you should get negative 0.262. All right, awesome. Here is a released item from a previous diploma. Point P, k comma 2, and Q, 2 comma 1/3, lie on the partial graph of y equals log base b of x as shown. What is the value of k? So one of the things, I'm just going to hide my face here just in case you need to see the full question. I don't think I'm going to be cutting that one off, but just in case. Okay. Very seldom in a diploma question are you going to be given information you don't need. Okay, that's not usually the purpose of a diploma question. So when given a question like this, you're always going to ask yourself, okay, why have I been given what I've been given? Usually there's really good reasons why you've been given what you've been given. So I want to figure out K, but I can't quite do that yet because I don't know what B is. So the first thing I'm going to do is I'm going to use this point here, Q, to solve for B. Okay, and I can do that by plugging this in for X and this in for Y. So I'm going to go 1/3 equals log base B of 2. And then if I switch this to exponential form, that becomes 2 to the 1/3, sorry, B to the 1/3 equals 2. Then I can cube both sides so that I could get 1/3 times 3, right? I'm taking a power of power. So that would just be B. 1/3 times 3 is 1. And then that would be 8. So now I know B is 8. Then I can use the next point, which is K comma 2, looking at that as 2 equals, just plugging in 2 in for Y, log base 8, I know that now, of K. Okay, switch this to exponential form, and I get 8 squared equals k, and so my answer would be 64. Okay. All right. Logs have identities or laws that we will work with as well, just like trig did. Yay. There are three main ones that are listed on your formula sheet. To solve, they are when you are taking the log of two numbers that are being multiplied together, you can expand that out to be separate addition of logs. When you're taking the log of two items being divided by each other, you can spread that out by subtracting the logs. And then I just actually 2 seconds ago alluded to your power log law. An exponent on a number that you're taking the log of, that exponent can come to the front of the log and it's equivalent. To solve equations using exponents or logs, you always have access to your graphing calculator. All your equations can be solved by placing the left side into y1 and the right side into y2. But remember, that usually is not going to fly on a written response portion. On a written response portion, you're going to want to do it some sort of algebraic way. If you're dealing with an algebraic approach, you have three options. The first one that you want to try is to make the bases the same. And then once you've written it as powers, a single power on either side that have the same base, you can pull the exponents out. Or you can convert between exponential logarithmic forms to undo something that's you don't want there. So like if you're trying to get rid of an exponent, maybe you could switch it to logs. Or if you're trying to, if the thing you're trying to solve for, if the variable you're trying to solve for is inside or trapped inside a log, you can convert it to exponential form and that will untrap it. Or you could take the log of both sides. Okay. All right. If log base x of y equals a, then an equivalent expression for y squared is what? So what I might do here, I'm just gonna get my ink going here. So y equals x to the a. Base became the base. Dude that was locked becomes free. Dude that was free is now locked. Okay. So that's an expression for y, but I want an expression for y squared. So I'm gonna have to square both sides. And that would give me y squared equals x. I have a power of power, so I multiply the exponents together, 2a. Okay. So, yay, we got it right. We're gonna rock our diploma. It's gonna be so awesome. Okay, if log base 5 of 2 equals a, and log base 5 of 3 equals b, then an equivalent expression for log base 5 of 48. I actually love doing these types of questions. What I essentially want to do is I want to break my 48 into 2s and 3s. Okay, because every time I can see log base 5 of 2, I can switch that to A, and every time I see log base 5 of 3, I can switch that to B. So I'm going to take 48, and I'm just going to divide by 3. That gives me 45. And nope, that was silly. I took 48 and subtracted 3. 48 divided by 3 is 16. I can't divide by 3 again, so I know I can take out 1 3. Then 16, I know is 2 to the 4, but if you didn't know that, you could just keep dividing by 2 until you see how many 2's you were able to divide out. Okay, so sorry, friends, that should not say plus right now. That's a multiplication sign. Okay, so I can expand this out to be log base 5 of 3. Now it's a plus sign. Log base 5 of 2 to the 4. Okay, log base 5 of 3 is b. The 4 comes to the front. And log base 5 of 2 is a. So I have 4a plus b, which looks like the answer C. Okay. Yeah. If this is a multiple choice question, the other thing you can do here is use the store function of your calculator. So on a Casio, you are looking for an arrow. It's just below your 10 button, and it's just an arrow that points to the right. On a TI, you would be looking for, it says STO, and it's kind of on the left column, okay? So what you could do is you could store a value in for A. So like go log base 5 of 2, figure out what that decimal is, and just store that as A. And then log base 5 of 3, store that as B. Then figure out what log base 5 of 48 is. And then in your calculator, type each one of these in, and only one of them is going to match the same number that log base 5 of 48 is. Okay, so that's another way to use your calculator to check your answer. Okay, awesome. If log base m of A is 3 and log base m of B is 4, evaluate log base m of 1 over AB. Now, this is a very similar question to what I just asked you. First of all, you want to think about the fact that this is 1 divided by AB. So I'm going to expand this out to be separate logs by going log base m of 1 minus log base m of AB. Then I know that log base m of 1 is 0. The log of any base of 1 is 0. And then I'm going to want to expand this AB. So this will be log base m of A plus log base m of B. But you got to remember that there's a negative in the front. Okay. So just because this becomes 0 doesn't drop that negative there. So you want to keep that negative there. And then I know log base m of A is 3 and log base m of B is 4. So that becomes negative 7 altogether. Okay. All right, friends. Awesome. If log base 2 of A equals B, then log base 4 of A equals what? Okay. So we're trying to change the base here. I'm going to show you this kind of in two different ways. First of all, we're going to say A equals 2 to the B. So what I did is I just took this and switched it to exponential form. Okay. Then if A equals 2 to the B, I can call my 2 4 to the 1/2. So I can say, right, because the square root of 4 is 2. 4 to the 1/2 is the same as the square root of 4. So I've replaced my 2 with 4 to the 1/2. And then I can say, okay, remember, why am I doing this? Because this guy says log base 4, right? So I am trying to think about what would the base of 4 look like. So then that's going to give me 4 to the B over 2. And then I just switch it back to log form. And I get log base 4 of A equals B over 2. So now I know my answer is B over 2. Okay, I'm going to show you another way though. One is not better than the other. It's just a matter of which one clicks in your head. Okay, so the other way to look at this is to say, okay, I know that A is 2 to the B. So I'm just going to go right over here and switch my A with 2 to the B. Okay, then the B comes to the front. And then again, I would make my 2 be 4 to the 1/2. The 1/2 would come to the front, and log base 4 is 1. So I'd be left with B over 2 again. Okay. So in this next little section that we're doing, starting on question 16 here, we're moving into solving equations now. Now, you'll notice in my introduction, I did give you a couple of examples on solving equations. I want to go through each one with you. The first kind of go-to would be, hey, can I make the bases the same? So when I'm looking at this, I want to say to myself, okay, can I make 343 be 7 to the something? So I can play around on my calculator a little bit to figure that out and go 7 to the 2, 7 to the 3, 7 to the 4 until I figure something out. It turns out to be 7 to the 3. So I can change 343 to be 7 cubed. Okay, now I have an exponential equation that's written as single powers of the same base equal to each other. Okay, that is a property in math. If I just get my ink flowing here, just one sec. That's a property in math that essentially says this: if x over 3 equals 7 over 3, well, then x has to equal 7, right? 2 over 3 doesn't equal 7 over 3. We apply that to fractions. We can also apply that to exponents. So if 7 to the x equals 7 to the 4, then x has to be 4 because I can't say that 7 to the 7 equals 7 to the 4. Okay, so when I have a single power and they're the same base, I can then say, oh, okay, then it's logical, it's mathematical to say that the exponents have to equal each other. Okay, now, just as a caveat, if I had said, hey, this is 1 plus that 1 plus would screw that up. I can't do that anymore. Okay, okay, so now I can say then that x minus 2 equals 3, and then I just solve for x. So I'm going to add 2 to both sides and say that x equals 5. Okay, same thing. We're just a little bit extra layer of complexity here. I know that 27 I can write as 3 to the 3. I know that root 3 I can write as 3 to the half, 3 to the 1 over 2. Okay, so this becomes 3 to the 3 times 3 to the 1 over 2. Then here I'm multiplying powers of the same base, so my exponent laws are kicking in, right? When I multiply powers of the same base, I add the exponents together. So that's going to be 3 to the 3.5, or I'm going to write 3.5 as an improper fraction. So that would be 7 over 2. And then look, I'm ready to pull my exponents out. I have single powers of the same base equal to each other. So I can just say, hey, that means x has to be 7 over 2. Okay, x has to be 7 over 2. Okay, one extra sort of layer here. We're going to get into some fractions. 27 and 81. I know both of those can be base 3. Okay, 3 to the 3 is 27, and 3 to the 4 is 81. Now, it's not 81, it is 1 over 81, and so I have to take that into consideration as well. Remember, again, back to grade 10, some exponent laws that we've got. A negative exponent will tell you to flip the base. So if I want 1 over 81, I can call that 3 to the negative 4. Okay, so I'm going to write this as 3 to the 3 to the x minus 2 and 3 to the negative 4 to the x plus 3. Now, here's where I'd like to offer you a little bit of encouragement from someone who has perhaps seen more questions than you have. At this stage, I always want kids to say, hey, I'm going to stop and say, okay, does 3 to the 3 equal what's directly above it? Does 3 to the negative 4 equal what's directly above it? Okay, that's super important because a lot of times what happens, especially when we're writing a high stakes exam, right, our stress level is a little higher. We often, our brain thinks about the right things, but then puts them together in the wrong spot, and you end up flipping the wrong guy. So it's really important at this stage of the game, just take a quick sec and say, okay, does what I have written equal what's directly above it? If it doesn't, you want to just rethink what you did. Okay, now applying some exponent laws, these are both powers of a power, so I'll multiply the exponents together. That's going to give me 3 to the 3 to the 3x minus 6. Don't forget the 3 applies to both. And 3 to the negative 4x minus 12. Okay, now I have powers of single bases equal to each other. I can pull out the exponents and solve that way. Okay, so 3x minus 6 equals negative 4x minus 12. So that's going to be what, 7x, and if I add 6 to both sides, negative 6, so x equals negative 6 over 7. Okay, x equals negative 6 over 7. Awesome. Okay, what I want you to see here is it looks like a quadratic. Okay, just hone in on that 4 to the x for a second. If this says 4 to the 2x, really that means it's 4 to the x squared, right? So I've got something squared minus 6 times the something plus a number. That's a quadratic, and I want to try and factor it. It equals 0 already, okay? Now again, we don't want to stress you out. If you want to do a substitution of that to make it look a little friendlier, totally fine. So we could say, hey, we're going to let 4 to the x equal a. And if we let 4 to the x equal a, then I'm looking at a squared minus 6a plus 8 equals 0. I'm going to try and factor that. Two numbers that multiply together to give me 8 and add together to give me negative 6 would be negative 4, negative 2, which means a is 2 and a is 4. Now, You just have to remember when you get down to there, you're not done because we weren't actually solving for a, we were solving for 4 to the x. So that means 4 to the x equals 2. And if 4 to the x equals 2, x will equal 1/2, right? The square root of 4 is 2. And 4 to the x equals 4, which would make that x value a 1. Okay, so my two answers would actually be 1/2 and 1. Okay. Okay. Now, the next few, we're just going to start switching up the types of questions so that I want to make sure I give you kind of one of everything you could see to make sure you're comfortable with everything. Okay. So here, what I want you to think about is the variable is not in the exponent. Okay. The variable is actually a base. So actually what I'm trying to get rid of right now is that exponent. But the easiest way to get rid of a numerical exponent is just to take it to the power of its reciprocal. Okay, the reciprocal of -3/5 is -5/3. So if I took both sides to the power of -5/3, this becomes a power of a power, right? When I multiply those together, which is what I do, that's the exponent law. When I multiply those together, I just get x to the 1, which is just x. So that will essentially isolate x for me. Over here, hey friends, we can do that one in our head. So the negative tells me to flip it, so it's going to be 1/8. The 3 on the bottom tells me it's the cube root of 8. So I know that the cube root of 8 is 2. So right now I'm looking at 1/2. And then the 5 tells me an exponent of 5 on that 2. So that'd be 32. So my answer is 1/32. Now, if that conversation freaked you out, stop, take a deep breath. You can, in your calculator, go 8 exponent -5/3, and it's going to give you the 1/32. Okay, don't stress about that. I just like doing mental math. Okay, good. Let's take a look at this guy then. Log base 2 of log base 3 of x equals 3. So essentially, forget about the fact that this says log base 3 of x for a second. If this just said log base 3 of something, sorry, log base 2 of something equals 3, how to unlock that is you would switch it to exponential form, right? Base would become the base. The dude that was by himself will now be locked. And then the dude that was locked will now be by himself. Okay, so that was my first switch. Then I can look at this again and say, oh, okay, but now I've got a base of 3. So 2 to the 3 is 8. So this can become 8. Sorry, my bad. I shouldn't have said two numbers at the same time because my brain got thinking other things. This will be 3 to the 8, right? Base becomes the base. Dude that was by himself will now become locked. And then dude that was locked will now be by himself. Okay. Now, let's also talk restrictions on this. When I'm taking the log of something, I have to take the log of a number that's greater than 0. So I would also want to say here, x has to be greater than 0. 3 to the 8 is greater than 0. I don't know what 3 to the 8 is off the top of my head, but I'll tell you in a second when I bring the PowerPoint up. 6,561. Okay. At some point, my mental math does cap out. I guess I could have, well, it's all good, never mind. Okay, we got this. 6,561, okay? All right. Okay, log base x plus 2 of 5 equals 10. So this time, the variable that I'm trying to solve for is actually locked in as the base of the log. First thing I want to do there is switch it to exponential form. Base becomes the base. So this will be x plus 2 to the something equals 5. So x plus 2 to the 10 equals 5. Okay. Now, rookie mistake. Sometimes when we're stressed, we make little rookie mistakes. A reminder that this 10 does not mean I just apply it to both of those as exponents. I can't do that. This is essentially the binomial theorem, right? This would be x plus 2 times x plus 2 times x plus 2 all the way 10 times. I don't want to do that. Instead, I'm going to take it to the power of 1/10. That will get rid of the exponent for me. Okay. Or if you like the 10th root better, if you like it that sort of language, that's fine too if you want to do it that way. Okay, but I took it to the power of 1 over 10, and then I'm just going to subtract 2. Now, I was not given any rounding instructions, so if I'm not given any rounding instructions, you're not supposed to round. You're supposed to answer in exact value. So this would be my answer in exact value, but just to make sure you're on the right track, I will give you the answer rounded to the nearest hundredth as well. So it would be about negative 0.83. Okay, so again, you should be doing this along with me, checking that you can press the right buttons in your calculator and all that sort of stuff. Okay, awesome, awesome. 7 equals 2 to the x plus 11. Okay, now my exponent has my variable, and I can't make this the same base, okay? So now I have to think of another strategy that doesn't involve making them the same base. And the easiest one here to do, I would think, is, I mean, you could log both sides, that's totally okay, and you'd be marked right. If you just want to look at one thing and just do it all the time, that's okay. But I'd like you to look at all the beautiful aspects of math. So we're going to convert this to log form. So base becomes the base, so I'm looking at log base 2. It'll be log base 2 of 7 because the 7 was free, so I want to lock it into the log, and that'll equal x plus 11. Then, to get x by itself, I just have to subtract 11 from both sides. So again, this would be my exact value answer. If I wanted to get a decimal approximation, it would be negative 8.12. But if the question doesn't say to give you a decimal approximation, don't. Okay, if the question doesn't say it, leave it as the log base 2 of 7 minus 11. Okay. All right, again, take a look at this. This is a quadratic, okay? I want you to see this as a quadratic. But side note, something to be careful of, don't think that this is the power log law where I can pull this to the front. I can't do that because the exponent is not on the x, it's on the log x, so that's different, okay? Okay, so let's talk restrictions first. I know that because I'm taking the log of x, x will have to be greater than 0. And now I'm just going to look at factoring it. In a previous example with the quadratic looking exponential one that I did a substitution. I said, hey, let's let 4 to the x equal a. You could do the same thing here. Let log x equal a and solve it that way. I'm not going to this time. I'm just going to go right into the factoring. But if it decreases your stress to make that substitution, totally go ahead and do that. Just make sure you're writing down that you're doing that, okay? It's really important that your work is followable to the marker. So if you want to make a substitution, that's totally okay, but you have to say log x equals a, and then go with that, or whatever your favorite letter is, okay? Okay, so I was just going to factor, I'm looking for two numbers that multiply together to give me negative 5, and add together to give me negative 4, and I know that's negative 5 and positive 1, okay? So I now am looking at the zero product principle because I have two numbers that multiply together to give me 0. Log x minus 5 equals 0, which means log x equals 5, which means x equals 10 to the 5, right? The base here is our common base of 10. 10 to the 5 is 100,000. Over here, I'm going to have log x equals negative 1, which means x equals 10 to the negative 1, or 1 over 10. Okay, now I take a look at those against my restrictions. My restrictions said that x had to be greater than 0. Both of those are positive numbers, so that's totally okay. Okay, so x equals 1 over 10 and 100,000. Awesome. Okay, now in this guide, I've got logs and numbers going on. So essentially, to get rid of the log, I need to convert to exponential form. But I can't convert to exponential form across several terms. So essentially, that means I need to get all the logs together as one log first, okay? So I'm going to take that negative log base 2 of x plus 2. I'm essentially just going to add it to both sides so that it's over here, okay? Before I do that, though, I want to have a quick little conversation about restrictions. This guy tells me x has to be greater than 0. This guy tells me x has to be greater than negative 2. Now, I want you to think about that for a second. Let me just draw a number line to help you out here. Here's 0. Here's greater than 0. You know what? if I'm going to help you out, I should be mathematically accurate. That should be a open circle. Here's -2, and so I'm looking at that. Okay. Overall, my restriction for this has to be x is greater than 0. Okay. I don't care that x has to be greater than -2 because look, like -1 is a perfect example. Yay, that's going to work in this one, no problem. But it doesn't work in this one, and so I can't continue with the question. Okay, so you're looking for the overall, sort of the most restrictive restriction. Okay, now it is still important that you write both of these and then conclude that overall x is greater than 0. Okay, you don't have to do this number line. I'm just trying to help you see visually why I'm suggesting that x is greater than 0 is more important. Okay. All right, cool. So we've dealt with the restrictions. I brought that over. And now I'm going to smush them together to make a single log. So I can deal with the single log by multiplying the separate ones together. So that's where the x squared plus 2x comes from. I'm now ready to switch this to exponential form. So it'll be base becomes the base, 2 to the 3 equals x squared plus 2x. 2 to the 3 is 8. I'm going to bring it over, and hey, I got a cute little quadratic to solve. Two numbers that multiply together to give me -8 and add together to give me 2. That would be, what, 4 neg2. Which means x equals -4 and 2. But hey, x can't equal -4 because of our restriction. And so we conclude that x equals 2. Okay, x equals 2. So the only thing in my work here, now that I'm looking at my work all together, if I was your marker, I would have wanted to see that you circled that guy to say that is the overall restriction. Okay. And again, I know I've talked about this in other contexts. You guys are going to get bored of me soon. Hey, thanks for sticking with me if you're bored of me. It is important that you state both of them and then state that one of them doesn't work. Okay. All right. That was awesome. Next up, 6 to the 5x equals 3 to the 2x minus 1. I can't make the bases the same. This one's a little trickier to convert to exponent or to logarithmic form because I've got exponents on both sides. So here's an example where I probably want to just log both sides, okay? Taking the log of both sides is just like adding 2 to both sides or squaring both sides. It's an algebraic process. As long as I'm doing it to both sides, I'm not changing the equality statement, okay? Now, I've actually done two things here. I've taken the log of both sides, okay? So that would look like this. And then I applied my power log law to say, hey, that exponent can now come to the front. Rookie mistake, make sure that this 2x minus 1 is in a set of brackets because lots of times kids write this. Well, even if you don't work with it like this, essentially you're saying the log only applies to the -1, and that's not what you mean. The log has to apply to both of those numbers. Okay, so just be careful with that. Hey, while we're here, let's have a conversation around restrictions. I'm not taking the log of a variable. My variable is up here in exponents. Anything goes for the variable. It can be negative, can be positive, can be rational, irrational, doesn't matter. Okay. Okay. So now I am going to get rid of that bracket. So I'm going to multiply log 3. Remember, log 3 is just a number. So I'm going to multiply log 3 by both sides. Okay. And then anytime we're doing algebra, the general kind of consensus of how to solve it is we get all our items that involve variables on one side, and we get all our items that don't involve variables on the other side. So because this 2x log 3 involves an x right here, I'm going to bring that over to the other side so that all the terms that involve x are on one side. So I just subtracted that from both sides. Now, I can't put these two things together, but I do see that x is common to both of them. And if x is common to both of them, I can factor out the x. That'll leave me with x times 5 log 6 minus 2 log 3. Now, this is messy, but it's just a number. So I just divide both sides by that number, and I've isolated x. Okay. Yeah. Couple little conversations I want to have with you here. The first conversation is exact value. Great. We'll just leave it like that. Rounded to a couple decimal places, you should be getting -0.16. A good thing just to pause me and make sure you can arrive at the same answer, just to make sure you're pressing the right buttons in the right order on your particular calculator. The other conversation I want to have, which is just kind of a fun conversation and just kind of a let's review log laws together, would be the following. Sorry, bear with me. I need to get ink turned on, and I just put my head in the way of my ink. Okay, there we go. So if I wanted to get this as a single log, just for fun, okay? So let's go negative log 3. I'm not going to touch that guy for a second, but on the bottom, I'm going to say that that is log of, I'm going to bring this guy up to be an exponent. I'm going to bring this guy up to be an exponent, and then I'm going to smush them together to be division. So that would be what? 6 to the 5 over 3 squared. You follow what I've done there? Okay, so I did two things. I applied my power log law, and then I smushed them together because I was subtracting separate logs. Now, just grabbing my calculator here, 6 exponent 5 divided by 9 is 864. So I could write that now as negative log base or log 3 of, or divided by, English. Me and English don't get along. Log 864. Okay, now, then I could write that as, I could use my change of base identity and say, hey, that's actually x equals negative log base 864 of 3. Okay, and now, just to prove the point, if I went to my handy dandy calculator, which I have just off the screen there, and type in log 864. Oh, it's negative. Let's put a negative in front. And that's going to be of 3. So, and I hit enter. I want you to notice. Let me see if I can get the glare off there. Okay, I get the exact same number there. Log, oh, great picture there. Log base 864 of 3. Okay. All right. Yay for us. So that was kind of fun. Clear my ink. Oh, no, clear my ink. Okay. Now, the last little section here is to get into applications, both exponential and logarithmic applications, okay? For exponential, we're going to look at this formula, y equals ab to the t over p, and everything I do with you will involve this formula, okay? With logs, it's a little different, but you don't have to stress about it because whatever formula you need will be given to you in the question. The exponential ones, the formulas won't be given to you because you can use this guy, and this guy is on your formula sheet. Okay, so just a reminder, your y is, oh, sorry guys, your y is your final value, a is your initial value, t is the total time that you're looking at, and p is your period time. So it's the time it takes to do whatever you're doing, whether you're doubling, whether you're decreasing by 10% or whatever you're doing. Okay, and then b is whatever rate we're talking about. Okay, so I had this conversation a little earlier in this note. Remember, I said you changed 100%, which meant you did jack all. Same thing here. So a 35% growth, b, well, first of all, 35% growth would be 135% change, but then the b value has to be a decimal, not a percent. So that'd be 1.35. Okay, just going to hide my head in case you don't have the words there. To grow, our rate needs to be greater than 1, and to decay, our rate needs to be less than 1. So then a 24% decay, really what I'm going to do there is go 100 minus 24, so that'd be 76%, and so my rate would be 0.76. Okay. Awesome. Okay. Bacteria doubles every 3 hours. I'm just going to hide myself for a quick sec. If the culture began with 24,000 bacteria, how many bacteria will be present in 5 hours? Okay, so I'm going to start with y equals a, b to the t over p, and I'm just going to start saying the things I know. I know my starting population is 24,000, so that'll be a. I know I'm doubling, so my b value will be 2. I know my total time is 5 hours and my period time is 3 hours. So I'll plug in 5 for T and 3 for P. And I just randomly stick that all in my calculator, okay? And I get 76,195. A quick little conversation here about rounding because rounding sometimes stresses kids out. Here's the easiest way I can say it, okay? First of all, it's highly doubtful your diploma is going to test you whether you say, actually, let me just, what was this number? 24,000 times 2 exponent 5 over 3. This number was actually 76,195.25, okay? So it'd be pretty easy to say that for sure we're going to end with 9.5. But let's just have a conversation about what if it said 76,195.9. Okay. Some schools of thought would say, hey, I round that up because we're not really talking about bacteria anymore. We're talking about like a statistical population. And we can use decimals for statistical population. And so then that would be 176,196. Others will say, oh, but 0.9 is not a living organism yet. And it has to actually hit that 1. And so we're going to leave it at 76,195. Okay. These are wonderful conversations to have. They're great mathematical discussions. Okay. They are not things that you should get stressed out over. Okay. Essentially, you have to think about contextual rounding like that if it just asks you a question. So like if it said, if my answer here was this 76,195.9 and this was the question, I would probably leave it at this answer because I didn't get a full bacteria, okay? But usually when we want to do like statistical rounding, it will say round to the nearest whole number or round to the nearest 10th or whatever. So if you're told you can round, then just follow statistical rounding, okay? If you're not told you can round, then you need to think about the context. So with human beings, you need to actually get past that whole number in order to use that whole number. With time, you often have to round up, right? Because if it said how many years is it going to take and your answer is 76.2, well, that means 76 isn't enough time. So you'd actually have to round that to 77, even though 2 is closer to 76, okay? But Alberta Ed is really good at making sure that the wording of the question tells you exactly what to do. So this is not a conversation you get stressed over. I know it's probably been a conversation you've had in your classes, but don't get stressed over it, okay? Okay, so good. Let's try another one. A small town has a current population of 42,500 people, and it's growing at an annual rate of 4.25%. Determine the population of the town 7 years from now. Okay. So first of all, my rate. I'm growing at a rate of 4.25%. So 4.25% as a decimal would be 0.0425. Now, that is not my B value. That would be a catastrophic plague on this population because 96% just died, right? Remember that to grow, I have to be greater than 1. So I just have to add a 1 to that, and then that will be my rate. Okay. Oh, I'm going to hide my head here in case you didn't get a chance to read that question. Okay. So I'm going to go back to y equals a b to the x. I can say t over p here. It's just that because it was every year, my p is 1. So I just didn't use it. Okay. So I'm looking at 42,500 times 1.0425 to the 7. And that's going to give me 56,875. 56,875. Right? Okay, you invest $2,300, earning interest at a rate of 6% per annum, compound monthly for 7 years. Determine how much money you've earned. Now, I'm going to hide my face for a quick sec. Okay. There is an alternate formula that you can use that some teachers still teach, but it's not on your formula sheet. So the first thing I want to do is just walk you through using this guy. Okay, so I invest $2,300. That's my start. Now, my rate is 6% per annum, but it's compounded monthly. So first of all, 6% would be 0.06, but that's how much I'm getting in a year. If I'm compounding monthly, what that means is every month interest gets calculated and gets put back on my investment. Okay, it's much nicer to compound every month because you are earning money on your interest even as quick as the second month. Okay, so what happens though is you get 6% in the entire year. So we take that 6% and we divide it by 12 because you're compounding monthly. Okay, so you only get a 12th of that each month. Now, remember, I also want to grow this investment, so I have to add 1 to it. Okay, so that's going to be my B value. Then my total time is 7 and my period time. Now, you got to be careful. We have set this up to be talking about years. My period is actually monthly, but I can't, the way I've set this up, I can't say monthly because I've started talking in years, and you can't switch your units in the middle of math. So if I'm talking years, I have to keep talking years. So if it's once a month, well, that would be 1/12 of a year, right? Because there's 12 years in a month. So my period is 1/12. Okay. Now, if I type all of that in, I am going to get the right answer. I'm going to quickly type that in for you because my PowerPoint is going to show you the other way to do it. But you get the same answer either way. And I just want to use it as a comparison. So 0.06 over 12. And then that's going to be, okay. Oh, I got a syntax error. Oh, I see why. Sorry. My bad, friends. My bad. Okay, so I get 3496.85. Now, the next quick conversation I want to have is that's not my answer. That represents how much money is in my bank account. I have to remember that the question said, how much did you earn? I did not earn that, at least not on this investment. Hopefully I earned it at another point. But as far as the investment goes, I'll have to subtract those two numbers to figure out how much I earned. Okay. Okay, now the alternate formula looks like this. Okay, again, if you don't know this formula, I wouldn't suggest you use it. I'm not into you memorizing something that's not going to be given to you, okay? But what I want you to notice is this actually is the exact same thing I just gave you, but we walked through it using the a b to the t over p. Now, you may look at this and say, oh, but Peter, it's not the same thing because you said 7 over 1/12. But hey, 7 divided by 1/12 is the same as 7 times 12 over 1, which is exactly what that's doing. Okay, so we're all good. Okay, so I plug all that in my calculator and I can see, hey, I get the exact same thing I just told you I was going to get, 3496.85. Now, a reminder, a couple of things. We're talking money. Money is not going to give you rounding instructions. You need to round to 2 decimal places, okay? Even if it said 0.2, don't you dare leave it as 0.2. It'd have to be 0.20. You always round to 2 decimal places, needs to be in cents. You need to have a little bit of sense about it. Okay, but remember, the amount you earned is what's in your bank account minus what was originally in your bank account. So final answer, 1,196.85. Okay, $1,196.85. Okay, the value of a car decreases at a rate of 16% each year. If the car was originally purchased for 21,000, just going to hide my big old head for a sec. Determine the value of the car after 6 years. Okay. And so that's going to follow the exact same thing. 16% decrease, so I have to go 100 minus 16. That's going to give me 84% for my rate. But then as a decimal, that would be 0.84. Okay, so I got 21,000 times 0.84 to the 6. And that's going to give me 7,377.26. Okay. Awesome, possum. Okay. A population triples every 7 years. I'll hide for a sec. Determine the time it takes for the population to double to the nearest hundredth of a year. Now, this is kind of a fun question because I never gave you a starting population. And in fact, it actually doesn't matter, okay? Call the original population 1, final population 2. I've doubled the population, okay? It doesn't have to biologically work. It just has to mathematically work. Okay, so I'm going to do exactly that. I called my final population 2, my initial population 1, and then I'm tripling every 7 years. So my rate is 3, and my p-value is 7. And now I'm looking for the t-value to make this population double, okay? So divide by 1, that's not going to do anything. So I get 2 equals 3 to the x over 7, and I'm going to switch that to log form. So base becomes the base. Dude that was by himself is now locked. Dude that was locked is now by himself. To get x by itself, to isolate for x, I'm going to multiply both sides by 7 and then throw that in my calculator. So I'm looking at 4.42. I just followed statistical rounding because it said to the nearest hundredth of a year. Okay. All right, friends, we got this. Let's head over to some log applications now. Now, remember, with log applications, each scenario is a slightly different formula. You don't have to stress about that. There will always be a formula given to you. Now, often with log applications, we're talking about some sort of intensity. Intensity would be this guy right there. Okay, and usually then your kind of mode of operation here is you want to rework this formula so that intensity is by itself. Okay, so even before I read this question, actually let me hide my head just so that you can see the top of that. Okay, pause if you need to before my head comes back. Okay, so if I was just gonna manipulate this, I would switch this to exponential form, so that would be 10 to the m. Equals I over IO. And then I'd multiply both sides by IO. Lots of kids get really stressed about IO. They're like, what's IO? It's essentially a reference or a base intensity. It doesn't matter what it is because it's going to go away in just a sec. So I have IO times 10 to the m equals I. Now, what I want you to notice about that is any sort of intensity comparison, what we often will then do is we'll take the larger intensity and divide it by the smaller intensity. Well, the larger intensity divided by the smaller intensity, what I want you to see there is I'd have IO over IO and my IOs would divide out. Okay, so don't stress about IO, it's going to go away. Okay, so let's read this question and see if we can kind of do a similar process. An earthquake in 1933 in Japan had a magnitude of 8.9. So that's my M value of that formula. The 1976 earthquake in Guatemala had a magnitude of 7.5. How many times more intense was the earthquake in Japan than the one in Guatemala? Round your answer to the nearest whole number. Okay, so here I go. I'm going to essentially sort of treat this like a systems of equations, but I'm going to have my magnitude of Japan versus my magnitude of Guatemala. So that's why I have J's and G's there. But I'm just going to switch this to exponential form. So I plugged in the 8.9 and then I went 10 to the 8.9 and then I multiplied by IO, just like I did on that previous slide. Okay, then I'm going to do the same thing over yonder and get a very, very similar statement. Okay, so often it's the stronger intensity divided by the weaker intensity equals the intensity ratio. Okay, so strong intensity divided by weak intensity is the intensity difference or intensity ratio. Now, it doesn't have to be like, it's all about perspective. So if I said, hey, I am 3 times your age and you're 20, you would automatically say that I'm 60 because you're like, okay, well, 20 times 60 is 3, or 60 divided by 20 is 3, right? So in that example, the strong dude, so I could go, the strong dude is actually the older dude. So we go 60 divided by 20 equals 3, and then I would say I'm 3 times your age. But I can flip that around and go like this and say, you are 1/3 my age, right? So the order doesn't necessarily matter. It's just matters of what you're comparing to what. Okay, so this one would say, I am 3 times your age. This one would say, you are 1/3 my age. Okay, usually we take the stronger and put it over the weaker. Okay, so back to our problem at hand. I took the stronger divided by the weaker. Here I can see, oh yay, my IOs go away, and I'm left with 10 to the 8.9 minus 7.5. When dividing powers of the same base, I just subtract the exponents. And that'll give me 10 to the 1.4, which is 25. So the Japan earthquake was 25 times more intense than the Guatemalan earthquake. Okay. See, that's not tricky. Okay. Gonna hide my head while I read this. An earthquake in Japan was measured to be 88 times as intense as an earthquake in San Francisco. If the San Francisco earthquake had a magnitude of 4.1, what was the magnitude of the Japan earthquake to the nearest 10th? Okay, so Japan was stronger, so I'm going to have Japan on the top and San Francisco on the bottom. I don't know the magnitude of Japan, so I'm just going to call that X. And very quickly, now I didn't manipulate that formula like I did on the last slide. I just went right to the intensity ratio. If this was on written response, you would want to manipulate the formula to get it to be I equals, okay, but since I just did that, I went right to the ratio here. So I have IO times 10 to the X, that's Japan, divided by IO times 10 to the 4.1, that's San Francisco, and I know that the ratio ends up being 88. So now I'm going to solve this. My IOs are gone, and this ends up being 10 to the X minus 4.1. And now I'm just going to solve this. Switch it to log form, so I'm looking at log 88, right? It's base 10. Log 88 is X minus 4.1, and then I just have to add 4.1 to both sides, throw that in my calculator. The magnitude of Japan would have been 6 on the Richter scale. Always make sure you have some sort of a concluding statement when you are doing some sort of an application. Okay. All right, friends, that's it for us. That's it for exponents and logs. In our next and last video, we will tackle permutations, combinations, the binomial theorem. But now you're set to go do the extra practice of your book. Remember, there's answer keys in that extra practice section. So hopefully that will help you. This has been a fun one. Hope you're doing good. Hope you're feeling good about your diploma. Again, thank you for sharing these videos. I super appreciate you getting the word out about these videos, and thanks for your subscriptions. And I will see you on video 11 for terms and cons. It'll be fun. Take care, guys.